Hello, my name is Ron Chan, and this paper is an application of quantum computing to power grid security. And we are going to target the conference 10th International Conference on Internet Technology. And in particular, we're going to hit three areas of that paper topics. One is situational awareness, the second is big data, and the third is national critical infrastructure. The first one, situational awareness, is important because for a power grid to know when something is going down, it happens very quickly, and quantum computing offers many advantages to situational awareness. The second is big data. There are tens of thousands of nodes on the power grid, and the algorithms to find out what's happening are classified as big data. And we come now to our most important topic, that's national critical infrastructure, and quantum computing offers a lot to reroute the power to keep the grid working for our infrastructure. So without any further ado, let me just introduce myself again. I'm Ron Chan. My advisor is Aspen Olmsted, and we are part of NYU Tandon School of Engineering. Let's ask what the motivation is to do this kind of paper. And what I saw was a blackout happened in August of 14th, 2003 that took out 8 states. And if you look at the graphic, there's Michigan, Ohio, New York, and parts of Canada like Toronto and much of Ontario. And in the peak of the avalanche, it's a cascading avalanche that just took one plant after another very quickly. In 45 seconds, 20 Lake Erie power plants suddenly shut down, which serviced 1.74 million homes. And this was the start of it, and as it progressed onwards, it eventually impacted 50 million people. This is actually a big, big deal. On December 23rd, 2015, in Ukraine, a cyber attack took control of a power distribution center. In moments, the attackers took down 30 substations, left 250,000 people in the dark. It all began with spear phishing, which opened some back doors, but they couldn't get control of the substation control panel. So what they did is they did some creative things to finally get the passwords of these operators. Once they got in, they used something like a remote terminal and took control of the operator's console. And now, thereby, the keyboard of the operators was useless, and the attackers just clicked on taking each substation down one by one just with a click of a mouse, and within moments, 30 substations were taken out. The key to both of these attacks is that a power station can be down merely in seconds, and hence why we need quantum computing to do this. The scope of the problem is actually quite large. If you look at the map over here, it's data from GIS plats, and it shows in one of the grids in America, the Western United States grid, that grid encompasses 13,000 nodes and 16,000 buses. This is a huge problem for optimization. Now, what also makes it difficult is that if you look at the state of the network at any one moment, the load state for the network is changing dynamically. And that means how the users are drawing power. The users have various load profiles, and it's unpredictable. Now, also the rate of generation is also unpredictable, where solar or wind or other means of hydroelectric means of generation of power, the influx of power is also unpredictable and dynamically changing. On top of this, we see that electricity travels on open transmission line at the speed of light. So in order to manage this problem, you have to manage it at or better than the speed of light, and the problem size is about 30,000 unknowns. So algorithms must compute the current condition of the nodes and balance the power across it over a large set of unknowns continuously. How do you do this? Now, because of the number of stations that were took down in 2003, people came up with something called a smart grid. And a smart grid gets away from centralized generation and moves into distributed generation. And the way to do that is to use these wireless sensors. And these sensors sense what's happening at the grid at any one time. But the key is to get away from a centralized generation where you take down the whole substation, but now you have much smaller distributed generators. How does this work? In a paper by Jerry Chadwick, she showed how microgrids um, segregate the problem into smaller localized sections. Each one of these have generation and storage and control, but also the loads are now over a much denser localized region than over a wide sector. So with these smaller microgrids, if one were to be taken out, the other microgrids can continuously feed power. Let's say there's a cyber attack over here. These other microgrids can, on this power exchange highway, continue to feed power into the affected microgrid, even if the actor took down this generator right here. So with these large array of microgrids, this is a much bigger problem for the cyber attacker, but also a much bigger problem in energy management. How do you do this? Here we use this concept of quantum computing. In December of 2015, TechTime announced that Google, which bought a D-Wave 2000 quantum computer, had solved an optimization problem of 1,000 variables 100 million times faster than regular computer chips. This is really significant that it could do something so fast. And that opens up a world of possibilities because these quantum computers can now potentially solve problems that classical computers cannot. And how does it work? It's because they're acting using parallel processing at a speed far greater than classical parallel processing. Let's look into it. Quantum bits. A quantum computer consists of this device right here, and whereas in classical computing information is either stored as a 0 or 1, in quantum computing the information is stored in these Josephson junctions that are cooled very cold down below 1 Kelvin, and they could be in various states. And when I mean states, I mean a probability density state, and there is a state, a ground state 0, and we call that in quantum mechanics bracket 0, and there is bracket 1, let's say an upper state, and now you have a linear superposition of the ground state and the upper state A and B. This superposition allows a qubit to be in an indeterminate state because A and B are probabilities, and we don't know the answer until the very last step of the algorithm where we measure the final state after our algorithm has finished. So while the algorithm is going, the range of possibilities, all these possibilities of the superposition are all calculated in parallel. So this provides for enormous speed up. Let's take a more detailed look at that. So let's say I have 3 qubits. 2 to the third is 8. So 8 states will be calculated in parallel. So now you can see this is an exponential increase in computing, whereas in classical computing you have to compute each one of these variables one at a time, whereas in quantum computing you're computing all of them at the same time, hence the parallel nature. One more concept only found in quantum mechanics and not in classical mechanics is quantum entanglement. Here shown in a graphic are 2 quantum particles, and these are entangled particles which remain connected so that the actions performed on one affects the other even when separated by a great distance. And Albert Einstein called this spooky action at a distance. The transfer of information from photon A to photon B occurs at a speed at least 10,000 times the speed of light. Why is that important? It's because if you remember, electricity on a transmission grid for power travels at the speed of light. So if there's a disturbance, we need to compute something much faster than the speed of light, and entangled particles provides that. What is the current record? Current record is 2 meters that these entangled particles are separated by, but certainly for power grid applications, we need this to be much, much, much farther. Now, there are many proposals in literature, and one is a proposal to sense earthquakes by using a pair of entangled photons. We put one photon in the ground to sense movement, and the other photon into an orbiting space station 310 miles away. So the moment that movement is detected on the first photon, on a photon that is up in the satellite, it receives that information faster than the speed of light, and it can now send it to the appropriate authorities for them to take action. So these entangled particles can sense grid problems way faster than the wireless network afforded by smart grids. One more aspect is machine learning. Darktrace proposed unsupervised machine learning to discover the pattern of life for every device and every user on the network to set what is normal. And what that is that it goes into organization and it discovers how do users use the internet and how do users use their system, and over time it discovers what is normal. Then events that are statistically distant can ring up as an intruder. That would be useful if we see an attack in process and we can immediately see something going on. Now that's for unsupervised learning where the nodes are maybe smaller. For larger number of nodes, we use something called supervised learning. And in supervised learning, we train data in such a way that we can classify them into one set or another set, and then we can infer, oh, it belonged to this side or that side, and we could classify the new data. How does this work for power grids? If all the voltages are within safe limits, we have then classified the data as being safe. So if a new voltage comes up, which is away from that classification, we can then see that belongs to another set. How do you do that? Well, let's look at the next slide. There is a technique in machine learning called support vector machine. And this is a supervised learning model used for classification. And what that does is it learns as it trains itself to determine if the data belongs to the first class, which could be this class right here, the gray dots, or on the other side of the line, these black dots over here. They do so by making an optimal hyperplane, and that's that red line we see here in 2 dimensions, but in many, many dimensions it's a hyperplane, and it divides the two sets into the lower and the upper regions. Now this can take hours and hours, especially for large numbers of variables. So we need to turn to something else. Peter Witek has a book on quantum SVM, and in that book he draws from a proof which is down here, quantum support vector machine for big data classification, which takes a m squared n problem, m being the number of training vectors and n being the number of features being considered, and it takes that m squared n problem and reduces it to a log mn problem. So now this is now subpolynomial in time, and it reduces the order by 1 order of magnitude faster than classical computing. That's exactly what we need to find out what's happening on the power grid. So now we get to the heart of our paper, and this is the algorithm in 3 parts. The first part is to find the grid status, find the current voltages and phases. At one moment in time, I need to see what my situation is. The power contains both real and reactive power. And why are there these things? It's because power is a complex entity. If you look at the real power, the real part is power supplied that's measurable and moves into the grid. But reactive power are these machinery that draw power away, and it is in the opposite quadrature, and it poos power from the power grid. So it is a complex number, and we need to find both the voltage and the phase of this complex number. The second step is anomaly detection. And once I know the state of it, I want to find, are there any outliers, things that um, look like they shouldn't belong. So this is where SVM comes in. And as an example, in our power grid, we can see circuit breakers which should be closed but are open, resulting in open voltages. And now we know something's going on in our grid, and that group of nodes is now not usable, and we need to do something about it. Well, what do? And that's our third step, rerouting algorithms. First of all, we need to load balance the entire grid, and if there are down nodes, we need to balance ourselves so that in the presence of islands of fault, we can still supply power to the microgrids and the users in those microgrids. Now, underlying all of these three is that we're using entangled particles to give us instantaneous status on voltages and phases for those that we can know, and those that we can't, we'll use something else. And of course, these algorithms must operate faster than the damage is created. Step one is to find the voltage and the phase. Here we look at the load. We have real and reactive for the load, and also we have generator power. We have real power for that, and we have slack power where the voltages and the phase are known. So our problem is for N buses and R generators, a 2N minus R type scope. What do? We solve the real equation and we solve the reactive equation. So you can see real power in here and reactive power over here. Now, if you look at the phase is contained in this cosine. And if you look at the voltages, they're contained in this product. So this is a nonlinear system of equations, and if some are unknown, it could become a linear programming problem, but it really is a nonlinear system of equations, and that takes a long time to solve classically. But a paper by Dowd showed that there is a quantum solution for certain classes of nonlinear systems of equations, and that could be used to provide great speed up. The second part of our algorithm is to check for anomalies, and here we turn to a paper called Joint Cyber and Physical Attacks on Power Grids, and here they use graph theoretic approaches. And why do they do that? It's because they want to find these disconnected regions, and that's perhaps in our case due to an attack. And once you find where these nodes are down, you don't have much information, so you have to use linear programming to find that out. Once we found that out, we can recover the phase information up to the point of where it was disconnected, and then we partition the grid into attack resilient zones where we can still route power and use power. We may augment this approach with other approaches using SVM to detect near catastrophic characteristics. Whereas this is finding things that are just completely down, here we're finding things that are about to go down. Something fishy is going on, and we use machine learning to find out what is going on. So we can use unsupervised learning here to discover something that detects the onset of failure in these nodes. Now, these are both in classical computing, and we would recast these approaches in quantum equations. For example, this disconnected equation region right here. To determine if n nodes are connected, we see that this problem classically is on the order of n squared. But Durr, in his paper, proved that a quantum algorithm can solve this in n to the 3/2, which is a big deal if n is very large, like 30,000. Now, the last part of our approach is load balancing. And here we're following a thesis by Patel using fuzzy logic to balance the nodes. And what do we mean here? It's that if some of the nodes have a lot of power in storage and other nodes don't, then when an attack happens, um, those that don't have much power could immediately take down the loads that they were servicing. Hence the need to balance the power across the node so that all the storage facilities all have a healthy amount of power. He used this equation right here, the real power here and the reactive power, to solve for this load balance. And it's a delta LB from one node to another, and it tries to level that delta across all of the nodes. So it's a optimization problem. Now, there are papers in quantum equations using adiabatic optimization to reduce the runtime. So in conclusion, let me give a few points. Number one, many of these algorithms involve incomplete information with large numbers of unknowns. To solve that will require n squared or m squared n type computation, which is really infeasible on the scale that we're looking at for power grid attacks. Now, we must use quantum effects. And the particular quantum effect we want to use is entangled particles, and that delivers instantaneous situational awareness for those nodes that are still viable. Quantum computing provides the most probabilistic solution as all 2 to the nth solutions are iterated in one step, leading to an n-fold increase in computation. And that's that one order of magnitude that we get, more than that, in fact. Presented in this paper is an integrated quantum approach to grid status, anomaly detection, and load rebalancing. And these topics are found in these other papers separate, but here in this paper we make an algorithm to unite these and provide quantum algorithm support for each of these. Thank you very much.